So, if you've ever felt a sudden wave of panic looking at a math textbook full of weird symbols, I want you to take a deep breath. In today's explainer, we're going to completely remove the fear from set theory. How? By just looking at pictures before we ever even touch an equation. Think about it, we actually use this exact math in real life, literally all the time. When you're hunting for a shopping discount that applies to both clothes and shoes, or maybe measuring overlapping plots of land, coordinating building design plans, or just checking which apps are draining your phone data, you're using set theory. As your guide, my goal today is to show you that you actually already know how this works intuitively.
Okay, let's dive right in by asking a really simple question. How do we organize our everyday world without getting completely overwhelmed? I mean, whether it's organizing your closet or figuring out who's coming to a party, our brains naturally categorize things into groups. It's just what we do. So today, we're going to apply a visual-first approach to harness that natural organizing power.
Here's our game plan for today. We'll start off by visualizing math with Venn diagrams. Then we'll look at combining everything with unions, finding overlaps through intersections, dealing with totally separate disjoint sets, spotting differences with set subtraction, and finally, we'll wrap up with a quick set theory cheat sheet.
All right, part 1. Seeing math, Venn diagrams.
First up, we're going to transform all that abstract math into some very simple drawings. Before we even glance at a formula, let's look at the actual shape of our math universe. Notice what happens here. We use a big rectangle for what we call the universal set. This rectangle, it's the ultimate container. It holds absolutely everything we care about for a specific problem. And inside that rectangle, we draw deep purple circles to represent subsets, which are really just smaller, specific groups. It beautifully frames our mathematical world, giving nice, clear boundaries to our problem.
And this brilliantly illustrates how a real-world scenario translates directly into math. Look at the left side. A teacher is tracking absent students. Roja, Ramu, and Ravi were absent Tuesday. Ramu, Preeti, and Hanif were absent Wednesday. On the right side, we just wrap those names in curly brackets. Set A is Tuesday's absentees, and Set B is Wednesday's. And that's it. That's literally all a mathematical set is, just a list of things belonging to a specific group.
Moving on to part 2, combining everything, union of sets.
Let's see how this builds. What actually happens when we want to combine everything together into a union of sets? Visually speaking, first, see how the union just means blending both circles together into one big purple shaded area? If we jump back to our teacher example, the union represents everyone who is absent on either Tuesday or Wednesday. We don't care which day. We just want the master list of anyone who missed class.
Now that we know why it works and what it looks like, let's look at the official symbol. The crucial point here is that this U-shaped symbol simply represents that combined purple area we were just looking at. It literally stands for union, so you just read A union B as A union B. Simple enough, right? Let's tackle an easy example together. First, we identify what's given. Set A has the numbers 2, 5, 6, and 8. Set B has 5, 7, 9, and 1. Next, what's being asked? We need to find A union B. To solve this step by step, we just dump absolutely everything from both sets into one big basket. But watch out! See that bright orange highlight on the number 5? The single most common mistake students make in exams is writing common elements more than once. The number 5 is in both sets, sure, but in our final answer we only write it down once. So our combined set is simply 1, 2, 5, 6, 7, 8, and 9.
Part 3. Finding overlaps, the intersection.
Now, what if the teacher only wants to talk to the students who are absent on both days? Visually, we aren't shading the whole thing anymore. We just zoom in on that small, football-shaped middle section right where our two circles cross paths. This shaded area represents only the things that exist in both groups at the exact same time. We denote this overlap with an upside-down U. Think of it kind of like a bridge connecting the two sets, capturing only the exact elements they share. This, my friends, is the intersection.
All right, let's step it up to a medium-level example. What's given here? Well, set A is 5, 6, 7, 8. Set B is 7, 8, 9, 10. What's asked? Find A intersection B. To solve this step by step, we basically act like detectives looking for a perfect match. 5, nope. 6, no. But look at 7 and 8. They live in both sets. Notice how they're isolated in bright orange right now? Our final answer is simply the set of 7 and 8.
You're doing great. See how easy this is when you just break it down visually?
Okay, part 4, completely separate disjoint sets.
But hey, what happens when sets have absolutely nothing in common? Sometimes sets simply refuse to mix. If sets have exactly 0 elements in common, like say a set of odd numbers and a set of even numbers, their circles are never going to touch. Visually, they're completely separate islands inside our universal rectangle. And because they have 0 overlap, their intersection is completely empty, which we call a null set. Mathematically, these are known as disjoint sets.
Part 5. Spotting differences, set subtraction.
Okay, take a deep breath. We're going to move to our final and admittedly hardest concept. But what's really fascinating here is the visual logic. When you see a minus b, it's not like regular math where you're just subtracting numbers. Instead, imagine you're holding circle A like a cookie. Now someone comes along and takes a bite out of it. That bite is any piece of A that also belongs to B. Whatever is shaded and left over is purely exclusively A.
Let's conquer a hard, board exam level example together. Given, set A is 1, 2, 3, 4, 5. Set B is 4, 5, 6, 7. Asked, find A minus B. Let's solve it step by step. First, we start with our base, set A. We just calmly list it out. Now, we check set B. Are there any intruders from B hiding inside A? Yes, the 4 and the 5. So we systematically erase the 4 and 5 from set A. What is left completely untouched? Just 1, 2, and 3. So our final answer is the set 1, 2, 3.
Now, before we wrap this section up, I have to point out a massive trap that so many students fall into on exams. In normal math, sometimes the order doesn't matter, right? But in set theory, it absolutely does. Looking at this visual comparison, it physically proves that A minus B is completely different from B minus A. A minus B is the leftover chunk on the left side. B minus A means we start with B as our cookie and take away A's bite, leaving the chunk on the right. Please never swap the order in a difference equation.
Which brings us to part 6, the set theory cheat sheet. You've done incredible work making it through all of that today. Let's lock in that knowledge. Here's your quick 5-point cheat sheet to translate any terrifying math symbol back into a friendly, manageable picture. 1. The rectangle is your universe. 2. Union is your U-shaped basket for everything. 3. Intersection is your upside-down bridge for only the overlaps. 4. Disjoint means isolated islands. And 5. Difference means taking a bite out of your starting circle. And as promised, here's your surprise trick to solve diagram questions way faster in exams. Whenever you're drawing a Venn diagram, always fill in the middle intersection first. Seriously, if you put the shared numbers in the middle first, you'll never accidentally double count them when filling out the rest of the circles. It literally works every single time. I'm going to leave you with a final intriguing puzzle derived from today's examples, just to test your new visual superpowers. Imagine drawing this out. If set A is entirely, completely inside set B, what does the Venn diagram for their union look like? Think about what happens when you combine them. The answer is surprisingly elegant. Think it over, and until next time, keep visualizing your solutions. And remember, you've absolutely got this.